For many years, enterprise IT organizations, with the help of their infrastructure teams, have been trying to optimize the hardware resources. The main challenge was always how to benchmark the workload and accordingly scale in and out based on the workload performance. Scaling in and out is not an easy task, especially on legacy infrastructure while dealing with monolithic workload. This is the promise cloud brings to the enterprise IT, to be able to build cloud-native workloads, a workload that is scalable by design and definitely with fast ignition and small footprint. Serverless is one of the cloud-native development models that is gaining more and more traction. One of the great values of serverless when it comes to resource utilization is the ability to create the right balance between workload needs and resource allocation. While in most other models, users have to deal with either over-provisioning or under-provisioning. In the case of serverless, we are able to provision the workload we need with the exact resources it requires. Serverless comes with built-in autoscaling with the help of knative pod autoscaler, KBA. KBA supports autoscaling based on number of concurrent connections, which is definitely representing the simultaneous requests that can be processed by each knative service revision. In case CPU and memory consumption-based autoscaling is required, serverless can be also configured to use the Kubernetes horizontal pod autoscaler, HPA. Let's see autoscaling in action. So here we have one knative service. First, we will edit the service. And as we can see, the soft limit, which is the autoscaling knative dev target, this identifies the number of concurrent connections the revision can take before it triggers spinning of new pod. So once we save the changes, as we can see, we start with 0 pods running. We go to our JMeter and we simulate number of concurrent users using synchronizing timer. So we have 10 concurrent users. And then the total number of threads, representing total number of users firing requests, 50. And this is the test result. So let's start the test. We go back to our service and we can see that immediately knative autoscaling was triggered, and we can see that 3 pods started and then scaled up till 12 pods. After some times all the pods will be running, so total 12 pods. And if we go back to our test, we can see that all the requests have been triggered and we got the response. So now let's change the soft limit and reduce it from 5 to 2. Means every pod representing a revision can take up to 2 concurrent connections, simultaneous requests. We save the changes, come back to the service, do the same test, and we can see that now the number of pods growing up to 32. And this gives us an idea about how the number of concurrent connections can control the number of pods, the revision instances running while we're getting the traffic hitting the knative service. So now let's go back and increase the number of concurrent connections per revision, and we start the test again, and we can see that now the number of pods was reduced to 3, and we're still getting the responses as expected. More important, talking about autoscaling, is to also consider the fast ignition, because it doesn't make any sense to autoscale workload that might take seconds or minutes to start. This is why it is really important to choose the right runtime, the right application framework to develop those serverless services. With the help of Quarks, for example, in this demo, we were able to start the Quarks services in average 28 milliseconds, having REST interfaces with some business logic to calculate or to do some calculations.